let me share my screen to the whiteboard. Let's continue from last time. We're almost done with chapter 4. Okay, we talked about some situation that Bernoulli doesn't work. Okay, Bernoulli is not almighty equation, work everywhere. No, it has a lot of limitations. Did I actually write it down? Okay, yes, limitation here for Bernoulli equation. It has to be steady state, incompressible fluid, inviscid fluid. That's a big assumption. Irrotational, that's a big assumption. Okay, so it doesn't work well in the rotational flow. Okay, it not doesn't work well. It totally doesn't work in the rotational flow. We give an example last time. We look at the hurricane eye between the hurricane eye wall and the hurricane center. It turned out to be center has the minimum velocity and the minimum pressure. Actually, velocity doesn't go inversely proportional to the pressure within the hurricane eye wall. Actually, velocity decreases to the center, the pressure also decreases. So they are proportional in the rotational flow region. Okay, so that's critical, very important. So in some of the situation, you need to know you cannot apply Bernoulli. If you apply Bernoulli, it's totally wrong. It's not just a little bit wrong, it's totally wrong, opposite. Okay, so be careful. So the final subject here we want to talk about is how do we determine the flow is rotational or irrotational? Okay, so the flow, most of the 90% of the time, you cannot see the flow. You don't know the flow. What does it look like? Okay, even you know what does it look like, actually, it's deceptive. Okay. For example, hurricane problem, again, between the hurricane eye wall and the center in that circle region, it is rotational flow. But outside the hurricane eye wall, too far away, that region is actually irrotational. It's not like looking at the flow. Does it look like a circulation or not? No, it's not. Okay, it's based on the deformation of the fluid element. Okay, if the fluid element deforms, okay, stretches, okay, then it's rotational. Let me draw this for you. So if the fluid element is doing like this without deformation, but change the position, it's called translation. It's just like if you going through a curvature trajectory, but without deformation of the fluid element, this is still irrotational. Okay, unless when you do the circulation, the fluid element actually changes the shape from one position to the other. For example, initial position is this, but when you rotate here, the element stretches and it further stretches during the trajectory. Then this is rotational flow. Okay, this is the complexity in the fluid mechanics. You can see, you can tell, okay, by your naked eye. Okay, so in the hurricane, I can see, hey, this is actually, there's a two region, inside the eye wall and the outside. Outside also has circulation, but far away from the eye wall. Okay, for the pressure velocity distribution, you can see actually, if this is position, this is the velocity. Velocity has a peak on these two eye walls, and it becomes zero, and then it becomes peak. Let's go down. And when it's far away, the velocity also reaches to zero. This velocity. Okay, so this is hurricane velocity distribution along this dimension. Okay, so velocity far away, you don't feel. You know, if a hurricane in Lake Charles, in Fargo, North Dakota, you won't feel that's the hurricane. So velocity is 0. So when you're getting close to the eye wall, velocity get the maximum. Okay, then when you go to the center, velocity decreases to 0. Then go to the other eye wall, it goes to the peak. Okay, so that region is rotational. Outside is irrotational. There's no stretch for the fluid element outside the eye wall. No deformation. Okay, that makes sense? So Bernoulli applies well in the area between the eye wall to far away. Outside the region, Bernoulli works. But inside the hurricane eye wall, Bernoulli doesn't. Okay? We proved it last time. No, Bernoulli doesn't work. Okay? Inside the eye wall. But outside it's okay. You can apply it. So the question is, how do we, this is a example, but in regular fluid mechanic application, how do we know it's irrotational and rotational? Many times we don't know, we don't see the flow, right? Okay, so again, come back to the origin. We said in fluid mechanics in the previous class, I said it's all about measure velocity. If you know the velocity fields, okay, you should be able to calculate such as acceleration. Another thing you can calculate is called vorticity. Okay, and if the vorticity, the value of vorticity, just similar to acceleration, vorticity is also a vector. Okay, if the vorticity is 0, okay, that means the flow is irrotational. Okay, if the vorticity is 0, if vorticity equals 0, irrotational. Okay, vice versa. If it's not 0, then it's rotational. Okay, so does that make sense to everybody? Vorticity. Okay, that's a new variable. Okay, new vector we're gonna introduce here. Okay, does that make sense? So you need to check vorticity. That's what I try to say. Okay, it's not just by looking at the flow if is this rotational or irrotational. It won't tell you. Okay, it's looking at it. It's deceptive. So vorticity is equation 4.40 in the textbook. It's a vector. Okay. Partial W, partial Y. See, it's similar to acceleration, right? It's derivative, velocity derivative. Partial V, partial Z, I. Okay, it's a vector form. So I have 3 components, I, J, and the K. Partial U, partial Z, minus partial W, partial X, J, and plus K. All right. Okay, so this is the definition of vorticity. It's a vector, so it's a vector format. It has X, Y, Z components, just like velocity and acceleration. Okay, acceleration, you have AX, AY, AZ. Okay, vorticity, it also has 3 components. Okay, so all of the 3 components has to be equals 0, then your vorticity is 0. Then it's irrotational. Okay, okay, that's very critical. Okay. So again, based on the velocity field, so it's so complicated to describe. It's hard to draw vorticity. Okay, but mass is your god now. You know, in fluid mechanics especially. Okay, let the value tells you. Let the math tell you what the outcome is, what the result is. So you calculate, you have the velocity field. Okay, assume that's the fundamental to any experiment you know into research for fluid mechanics. You need to measure the velocity field first, everywhere, velocity everywhere. So you should be able to get the gradient, velocity derivative everywhere. Okay, so then everywhere you can calculate the vorticity, just like you can calculate acceleration everywhere inside the flow field. Okay, every point. You still remember we practiced acceleration, right? Okay, so this is 3D. Okay, so sometimes we do 2D problem. If it's 2D, let's say you have U and V only. Okay, so what does the vorticity look like if it's 2D? This is basically the cross product, right? Velocity is a cross product of the delta cross U, right? Velocity. So if the U V only, so you see W partial Y is 0, partial V partial Z is 0, no Z, right? So and the second term J partial U partial Z is 0, no W partial X is equal to 0. So I and J both 0 if it's 2D. So you have vorticity only in the K third dimension, right-hand rule. You see, your rotation is XY plane, your vorticity goes to vertical. Okay, so then it will be only this. Okay. Did everybody follow me? Okay, so you have to go through this to determine if the flow is irrotational or rotational. Okay. This term has to be non-zero if it's 2D. Is that right? This is, you see, partial V, partial X. V is the Y component, but in the X derivative, right? Minus partial U, partial Y. Okay. Okay, let me give you an example. Okay, example. Let's say, hey, we have a flow problem. Okay. Bottom is wall. Okay, a fixed wall in the bottom, fluid in between the two plates. The top plate moves. Let's say 3 meters per second. Okay. Let's say distance between the two plates, 1 meter. Okay. Gap distance 1 meter. So let's say this flow is linear. First of all, does that make sense to you? If it's the flow is linear, let's say you have a non-slip boundary condition, right? So in the bottom, velocity is 0. In the top, velocity follows the plate, moving plate velocity. Okay, so the velocity vertically linearly change, fully developed. Okay, just like this. Okay, so physically, does that make sense to everybody? Well, in the reality, probably is not perfectly linear, but let's assume it's linear. Okay. Okay, so the question is this flow rotational or irrotational? Come on, it's a straight flow. Okay, so flow inside is just straight. Okay, your vector in between the two plates, the velocity is just straight. You don't see any circulation in this flow. It's just straight flow. No V. No vertical velocity. So inside the entire domain is just X direction velocity U. Okay, so U change linearly from the top plate to the bottom plate. that make sense, everybody? Okay, good. So before you take the fluid mechanics class, you don't know this one. You will say, probably say, you see, this is irrotational. I can apply Bernoulli to it. Okay. The answer is no, it's not a irrotation. It's a rotational flow. We're really against your intuition. It's deceptive by looking at the fluid mechanics, by looking at the flow. It's not true. Okay. And if you apply Bernoulli to this problem, it won't be right. Okay. Let's say how the heck it become rotational flow? It just seems like straight flow everywhere inside this channel. Okay. It's proven actually there's a huge deformation for the fluid element in there. Okay, to force it go straight. Okay, so let's see, how do we do it? We are going to use this equation, right? But if you use this equation, you need the expression for U and V for this flow regime, right? What is the expression for U and V for this? Well, V is 0. Everywhere is 0. I already know. Okay, so partial V, partial X is also 0. Okay, no problem. Okay, how about U? U changes, right? So can you determine a, we did it the last time, you remember? Linear function. How do you create the linear function? How do you determine the linear function? What does the linear function look like, first of all? So let's say this is the y dimension, right? This is the y dimension, right? So velocity change with y only. Okay, it's fully developed. It doesn't change with x. Do you agree? Okay, so can you write down the linear equation for velocity in terms of y? So u is a function of y and a function of y only. It is linear. What does the linear function look like? Anybody?
Something times x plus b.
Say it again.
So, some kind of slope times the x coordinate plus b.
There's no x coordinate. Listen carefully of what I said. It's u is a function of y only. Do you agree?
Yes, sir.
Okay, so can you actually write down the mathematical form for me? It's it's a linear function of y. What does it look like? Use letters. Hey, don't be afraid of using letters. If you don't know some value, give a letter. Is it Devin? You said it, right? You know it. Just write it down for me.
So it'd be u times y plus something.
Why is u times y there? U is left-hand side, right? U is function of y. So something times y, yes, first order. Then what times y? Linear function. You need to know, okay, what does the linear function look like? You said it right, some slope times the unknown, right? You said x, but I said, I correct you, it's not x, nothing to do with x in this problem. Velocity u is a function of y. So can you give a letter for the slope? Don't be afraid.
M.
Okay, m. Is that right? My? Anything else?
Plus an intercept. So plus b.
Plus b. Okay, yeah, don't be afraid. Fine, write it down. Use letters. If you don't know the value, put down the letters. Okay, I feel you really, many of you lack of this. You're afraid of write down stuff because you don't know the value. I don't know the value either, but don't be afraid. Write down the equation. Start from the equation. You can calculate those values. Okay, so your u is my plus b, right? Everybody agree? This is a linear function. So in order to calculate our vorticity now, you need to exactly find out what is M and the B. Do you agree? Everybody? Devin?
Yes, sir.
Yeah, you find a MB, then you can take a derivative partial U, partial Y. That's it, right? Okay. So your goal is to find M and the B. Okay, that's today's pop quiz, 2 points. Find the M and the B right now for me. Okay, the information you know is Y at Y equals 0. What is your velocity? Everybody? What is the velocity when Y equals 0?
0.
0, right? That's one condition. What is the other condition? At Y equals to 1 meter, the top surface, what is the velocity equals? Anybody look at the drawing. What is the velocity equals at the top wall, top
It's
surface?
3 meters per second.
3 meters per second. Okay, so you have 2 conditions. Okay, so find the M and the B for me. Okay, right now I'll give you 5 minutes. Okay, let me turn on the summation side. Very easy problem, right? I assume everybody know how to do it. If you don't know, practice it. Okay, 2 points.
Professor, so we're finding the slope.
You're finding M and the B.
Okay, thank you.
Okay. Okay, I give you 8 minutes. Okay, so 10:05 is the deadline. It's now is 9:58. So summation is open now. Hey, please turn on your video camera. It's a quiz. Only a few of you turn it on.
I already turned it in. Can I get up to go grab some?
Oh yeah. I will be back. I will start talking 10:05. Okay. Yeah, I think it's time to submit.
Yeah, Professor,
Yeah.
I'm gonna be submitting from my phone that I'm using right now, so I may be off.
Yeah, it's fine. That's fine. Yeah.
Dr. Zhang, I'm not sure why, but every time I try to submit, it gives me like a little red no sign.
Okay.
Over-
If you're unsure, just email me.
Okay, I'll do that.
Yep. Almost done. 10:04. Give me a sum up if you're done. Good. Bless you.
Thank you.
Okay. I guess it's time. Everybody? Anybody still working on it? Let me see. All done? Okay. Good. Let's wait for my clock to jump to 10:06. Okay. Okay, yeah, 10:06. Okay, summation close. Yeah, this is the reason I gave you a quick pop quiz today and previously. Also, once I remember, this is a very important skill I need you to have. You can you can estimate a linear function or maybe even second order, third order. Okay, but with boundary conditions, with the known informations, you should be able to determine, calculate the coefficients. That's why in the beginning I said, don't be afraid of writing letters. If anything, and you don't know, put a letter there and use the existing condition to determine those letters. Then you find out actually the expression. Okay, so obviously we can use these two conditions. 0 equals to m times 0 plus b. It turned out to be b is 0. Okay, then for the second condition, 3 will be equals to m times 1 plus b. B is 0. Okay, so m equals 3. Okay, is that what you got? Everybody gets a 2 point, right? Yeah, that's my goal for everybody to ace this class. Okay, don't get me wrong, I'm with you. Although I have to grade you, give you credit, give you score, but I'm with you. I hope you can ace my class. Okay. So the equation now, you know, velocity now I determine the m and the b, so it will be equal just 3y. U equal to 3y, right? That's the expression for this flow field. Okay, now we come back to the question, hey, is this flow rotational or irrotational? What is your magnitude of vorticity? Partial V, partial X. Vorticity magnitude, let's say, equals, it's a vector, so we need to talk about the magnitude, okay? So partial V, partial X, what is the partial V, partial X? 0. Minus partial U, partial Y. What is partial U, partial Y? We determine the expression. Hey, this is our expression. U is equals 3y, right? What is partial U, partial Y then?
Zero.
Partial U, partial Y is 0?
Is it 3?
U equals 3y.
Sorry, my mic got unmuted. I was talking to my boss.
Oh, okay.
3.
3, yeah. So your entire vorticity, overall vorticity magnitude is -3. Okay. Actually, the unit is like a meter, 1/2 Okay, that's the unit of the vorticity. Meter per second divided by meter, right? So it's 1/2. So you have a non-zero vorticity for this straight flow problem, which means it's kind of like weird, right? It's straight. Flow is totally straight, but it's rotational flow. Okay. Okay. Be careful. Okay. If it's rotational flow, Bernoulli doesn't work. Bernoulli doesn't work. It's so critical because Bernoulli is a easiest weapon, solve fluid mechanic problems. Okay, it's a weapon. It's a very nice weapon. It's a very nice knowledge. You want to apply Bernoulli to many of the problems, as many as you can, but it has to be irrotational. Like this problem is rotational. Okay, it doesn't work. So this is a process you need to take. Okay, you need to check. So vorticity. I introduced vorticity here. I think the textbook introduced the vorticity here in chapter 4. Serve this purpose. Okay, just let you know. Just want you to remember there's something called vorticity to tell if the flow is rotational or irrotational. Okay, then the reason we need to know the rotational or irrotational is to to know whether you'll be able to apply Bernoulli or not. Okay, so any questions before we move on to chapter 5? I think that's it for chapter 4. We've done it. Chapter 4, it's about, that's the first chapter for fluid dynamics. Okay, you start with introducing the velocity field. Okay, velocity always in fluid mechanics, it's not just one velocity value, it's velocity field. Hey, Dylan, you have a question?
Yes, sir. The
Yeah.
quiz that's happening Thursday, is that going to be on chapter 4? Or is that going to be on chapter 5?
Oh, chapter 4, of course, only chapter 4. I posted the homework in the break. I posted the first set like 2 weeks ago. The second
Yes,
set of
sir. Yes,
homework.
sir.
Yeah.
Yes, sir.
It's only
I
for
seen
chapter
that.
4. Yeah.
Yeah. It was just like you were finishing chapter 4 today. The quiz on Thursday, you know, we started chapter 5 today. I thought it was going to be on chapter
Yeah. It's chapter 4. Chapter 5 will be later. Okay.
All right.
Yep. Okay, so let's start chapter 4 with, I'll give it a quick review, with introduce the velocity. I think the point you need to remember here is velocity is not just one value in fluid mechanics. It's a velocity field. That's why we introduced the vector form. Everywhere has a different velocity most of the time. Okay, depend on the space of interest. Okay, in that space, everywhere has velocity. It's just not just one velocity. Okay, that's why you need to think about putting a grade in the space. Okay, on the grid point, you can calculate, find the velocity, so you kind of know what the velocity field look like in the inside the domain, inside the space. All right. Then acceleration, same thing. On every point, you have an acceleration. Since you have different velocity everywhere, you have different acceleration everywhere inside your space. Okay, so we have an equation to determine, okay, what is the acceleration based on velocity. Same here, vorticity. Everywhere has a vorticity value. So you have to determine vorticity by use that equation, okay. Then we know the acceleration, we introduce the Euler's equation to relate acceleration to the pressure, which is the most important to us, right, pressure. Then we derived a little bit from Euler's equation to Bernoulli equation. We don't like to use acceleration to relate to pressure. It's more indirect, right? Acceleration. More direct would be your velocity, you know? So Bernoulli relates velocity with the pressure, okay? Eventually we talk about, hey, Bernoulli is not, you know, universally work, okay? So in some situation like a rotational flow, Bernoulli doesn't work well. So we need to determine what is a rotational or irrotational, whether the flow is rotational or irrotational. Use the vorticity. Non-zero vorticity is irrotational. Okay, so see, give you a taste of fluid mechanics. Everything is mass. Okay, everything you have to rely on your equation and the solution you get from the equation to understand what's the physics. Okay, that's why I always like you to do experiments to verify it. Okay, it's equation is so important. You know, that's your God, your Bible. So verify equations using experiment. That's a lot of. It's not only this class. In the reality, a lot of times you need to do experiment to make sure the equation works. Okay. So chapter 5. Conservation of mass. It's the first conservation law. Okay. In order to study those conservation laws, we need to introduce a concept called flow rate. Okay, you heard about flow rate? We talk about flow rate even in the previous chapters, right? In industry, in whatever you work in the fluid mechanics, always, you know, talk about flow rate, pressure, flow rates. Okay, so what is the flow rate definition? Flow rate, let's say, first of all, volumetric flow rate versus mass flow rate. Mass flow rate. We use the letter Q, capital Q, to represent the volumetric flow rate. We use lowercase m, put a dot on top of it. We use that by convention, we use that m dot to represent the mass flow rate. Okay, so the relation between the mass flow rate and the volumetric flow rate is really simple, not much. Rho times Q. Okay, so cubic meter per second, that's a unit for volumetric flow rate. Kilogram per second, that's a mass flow rate, mass per time, and volume per time. It's cubic meter, or cubic feet per second, right? Or pound mass per second. Okay, so between the mass flow rate and the volumetric flow rate is easy. Okay, it's just the density. And the flow rates, volumetric flow rate is volume per second. Think about that. You have a tank to fill. You open the faucet, the water stream coming out. Okay, it's what flow rate may tell you every second how many volumes of water goes into the tank. Okay, so basically that's what it means. What does volumetric flow rate mean? Volume per time. If you convert it into mass, it will be mass flow rate. So it tells you how many mass goes to the tank every second. Okay, so that tells you so you can actually measure the flow rate easily. Okay, so the relation between them is just density. In this class, density is a constant. We are talking about incompressible fluid, right? We are not talking about compressible fluid. So density doesn't change. Density always a constant in our problem. So the relation between the two flow rate basically is just simple. Nothing, it's just a rho. Okay, rho times Q is m dot. Okay, so the Q will be a middleman. So the Q has to be, we're from velocity. Think about it. We talk about everything start with velocity, right? How do you convert the velocity into the flow rate? That's a task here, right? Do you know the equation? Anybody? Velocity times what is flow rate?
Cross-sectional area.
Yeah, velocity times the cross-sectional area. A is a cross-sectional area, where the velocity go perpendicular through. Okay. But this is the major assumption here is uniform flow. On the cross section. Just like pressure and the force. Remember, pressure times area equals force, right? Do you remember this? Also, we talk about that in the hydrostatics. Okay, if the pressure is uniform on the surface, pressure times area equals to the force, right? Same thing here. If the velocity is uniform on that cross section, for example, you have a pipe. Okay, when you do pipe flow, you talk about flow rates. Right? The flow velocity goes through the pipe, one of the cross sections. Okay, if the velocity is uniform on that cross section, I didn't say the velocity is uniform along the pipe. Be careful. Listen carefully to what I say. I said the velocity is uniform on the cross section. It still can change from place to place in the pipe. But on any given cross section, if the velocity is uniform, is constant on that cross section, okay, then you can use this equation, Q equal to V times area, to find the flow rate at that cross section. Does that make sense to you, everybody? Okay. Is that right? Any questions? Is that clear? Okay. So uniform velocity on the cross section, easy, from velocity to volumetric flow rate, then from volumetric flow rate to mass flow rate. Okay, you can convert back and forth. Okay, so that's a small portion of the word, very easy. Okay, uniform flow, but in reality, in a lot of situations, the velocity is not uniform on that cross section. Okay, it's not uniform. So what do we do? Do you still remember in the chapter 3, we talk about pressure when the pressure is not uniform on the area? How do we do? Okay, unfortunately, you have to deal with it. Okay, integration. You have to integrate the velocity on that area. Okay, you have to do the integration to find out the flow rate because the velocity is not uniform on that cross-sectional area A. Okay, so that gives you a little difficulty. Okay, so it's not straightforward. That's why you need an engineering degree, right? Be an engineer. Okay, you need to know those math calculus. It's a fundamental. Okay, let's do an example. Let's see. So for example, let's say, hey, you have a pipe, circular pipe. Let's say your velocity is not uniform, parabolic. Okay, parabolic. Okay, it's a circle. So your velocity is a function of r. This is a cylindrical coordinate, right? Flow direction, let's say x, right? Then the r direction, theta direction, right? Cylindrical coordinate. So your velocity is a function of r. I don't care what exactly function, but it's a function of r, right? It changes with r. Is that right? Okay. So how do we get the flow rate? So it said, hey, velocity equals, okay, how do you do dA? So that's my question. It's v. Let's say in this problem, we have only x direction velocity u, function of r, okay? How do you construct the dA for a circle? dA equals to what? What is dA? In terms of r. Hey, come on, you did the calculus, right? This is the typical problem for integration along a circular surface. What is this expression for dA in terms of r, in terms of dr?
Pi r squared.
dA equal to pi r squared? It's dA. It should be d something dr, right? I want the complete correct form. dA equals to what? You have to turn this into something dr. You see the integration here. You want to turn this into something dr, then you can integrate velocity out, right? Integrates the velocity out to the flow rate. Is that right? So you have a dA here in the integration doesn't work, right? You have to convert dA into something dr. Is that what we learned in calculus? Come on, guys. Still remember? You said pi r squared, what? Continue. I want you to have a correct, complete form. Josh, right? You said it, right?
Yes.
So what is
Would be
that?
the integral from 0 to r.
No,
of
not
pi-
the integral. Hey, come on.
No integral.
Convert the dA into something dr. Okay, give me the expression before you even try to do the integral. These are steps you need to take, right? Here, I want a dA, right? The
Changing a, so
dA equal to something dr, right? Something what dr? It's not equal to dr, right?
d pi r squared.
You mean pi r squared dr?
Yes.
I want you to say it. Say the complete correct sentence here, because in the test you have to write down correctly. You cannot make any mistake, right? So
Yeah, pi r squared is dr so that we can integrate it.
okay. So first of all, this is not correct. Okay, you always remember pi r squared dr, but in circular integration, it's not like this. So usually as a circle, you need to have a dA defined, right? dA, what does the dA look like? in that area. Does it look like this, dA? Only when you know what is your dA looks like, then you can put down an expression. dA equal to something dr. Is that right? I don't think so. Okay, this is not what we learned in calculus. It's not like this. Okay, your dA is actually, this is R, right? It's actually a ring. Infinitely thin ring. Guys, do you remember this? Okay, so what is the dA equals? I'm teaching calculus here. Okay, can you give me the expression for this ring, area of this ring? First of all, what is the thickness of the ring?
Like R2 minus R1.
No. Thickness is the dr. This is infinitely small element you define for dA. Okay, thickness, see, along the R direction. From the internal circle to the external circle, the difference is dr, delta R. Is that right? So it is delta R. That's the thickness of the ring is dr. So first of all, do you know the dimension, radial dimension R for a circle? That's the D, that's the R direction, right? The arrow. Okay. So the thickness between these two circles for the ring is the delta R. So how do you calculate the area of this ring? Is that the circumference of the ring times the thickness of the ring? Is that right? You need to know how to engineer, right? You need to know how to calculate the area of the ring, right? If the thickness is infinitely small, you can just use the circumference times the thickness. Is that right, everybody? So what is the circumference of that ring? Arbitrary element dA. So for this ring, you have a R, right? Any given R, because the ring is any arbitrary position. So what is the circumference of this ring? Come on, geometry, circumference.
2 pi r.
2 pi r, yeah. What is the thickness of this ring?
Two pi r2 minus 2 pi
No,
r1.
listen. What is the thickness? Look at what I draw. Pay attention to what I write and what I say.
dr.
Yes, the thickness is dr, right? That's what we defined
Oh,
here.
yeah, we already said that.
Yeah, I already said it on this. So this is the relation, okay? How do you convert dA into dr?
Integrate.
Okay. Yeah, is that good? Then, see, I wish I'm the calculus teacher. I can use practical problems to teach calculus concepts. Okay? So that's the flow rate. Then you can integrate it out, right? Everything inside the integration is something R, constant and R. U is a function of R. You can write down the expression for U in terms of R, okay? So something R times 2 pi R dr, then you can integrate it out. Is that right, everybody? Okay, you will have a homework assignment for calculating the flow rates, okay? Yeah, you need to know, okay? There might be quiz problems too. And in the final exam, come on, it's the basic flow rate you need to know how to calculate. It could be problems related. This is really the fundamental, okay? You need to know how to integrate the velocity dA into flow rate. Okay, then my question is, do you remember how to do integration? Okay, you have to. If you don't know how to do it, I really don't have much time to teach you detailed integration. Okay, you need to figure out. Okay, review your calculus and remember how to do integration. Okay, so this is the flow rate. I guess that's it for the flow rate. So based on I think the volumetric flow rate is the key. Okay, between volumetric flow rate to mass flow rate is really easy. Just a density. Okay, you can convert easily back and forth. But when you calculate the velocity to the volumetric flow rate, then depend on the velocity uniform or not. If it's a uniform velocity, easy. Okay, sometimes in industry application, we use the mean velocity. Hey, let's say, hey, this is the mean velocity times area. Okay, we don't care about the velocity change. Okay, assume it's uniform. So then just velocity times area. Okay, if in some application you need to really consider the non-uniformness of the flow, then you have to take integration velocity dA, and then it depends on the shape. This is 2 pi r dr. This is not right. Pi r squared is not right. It's 2 pi r dr, right? It's for the circle. What about its ellipse shape? Elliptical shape. So you need to figure out what is the dA for elliptical shape. Okay, if it's a rectangle, what is the dA in terms of dx and dy? Okay, so that's the point. Let's look at let's see, do I have an example in the textbook about flow rate calculation? We should, right? Okay, I think there are a couple. Circle, yeah, indeed, there's a circle. Let's do the calculation. Do we have the expression? Let's see. Okay, this is just average velocity. Okay. Okay, let's do 5.3. Example 5.3. Okay. This is the river. This is the seabed. You have the velocity distribution vertically, like this. Height is d. Okay. This is y dimension again. Velocity is the function of y. I think it has the expression u max times y over d half. Okay. Am I writing it correctly? Okay, yeah. So d is 2 meters. U max, I think, is in the top of the surface, has the maximum velocity. U max is what? 3 meters per second? Okay, no. And channel width is the velocity, it is 3 meters, right? 3 meters per second square.
It is.
Yeah, 3 meters per second. Okay, so the channel width in the paper dimension, the width, the channel is like this, right? The width is 5 meters. Okay. Okay. What is flow rate? How do we do? Is this a uniform velocity in the cross section? No, I see you shaking head from many of you, right? So it's non-uniform velocity. Go, no, I have no way. Just okay. You have to calculate the integration. Okay, so what's the task? To convert dA into dy. Look at the velocity function for y only, right? Okay, now it's not a circle. What is the conversion? So you need to know what is the small element dA look like for your shape. So that you need to memorize. For different shape, the dA is differently defined. Okay, need to memorize. For this rectangle shape, bear with my drawing. It's a rectangle. This is the y dimension. Okay, this is the 5 meter width. Okay, the height is 2 meter, right? Okay, what does the dA look like? Is a vertical band or horizontal band? Okay, to area integration, you really need to know what is your dA. Okay, it is a horizontal band here because you need to know dy, right? You need to use dy. What is dy? This is the y, is the thickness, is the height of the band dy. Okay, you have to follow dy, then you create your small element. The thickness is dy. Okay. So what is dA equals? Give me an expression to calculate the area of this small element dA.
Wouldn't it have to be the 5 meters dy?
Yeah, correct. 100% correct, Arthur. Okay. Do area integration is basically this is the key. You need to determine the dA. Okay, what does the dA look like? The hint is from what do you want? You want a dy, right? In your integration, u is there, so you need a dy. You use the function y, so you need dy. You also need to draw this dA with dy in there. Okay. The dy is this thickness, right? Okay. So Q basically equals to, you have a distribution velocity, right? So 3 times y over 2 square root integration phi dy. And what's the limit for y? Now you need the limits, right? It's a definite integration, right? What are the limits for dy?
Zero to d.
What is the d? Is d given?
It's in your drawing. It is. It's the
So-
height. It's the height of y.
So give me a value. What is the top limit?
Oh, 2 meters. 0 to 2.
0 to 2. Okay. Can everybody do this? Hey, flow rate calculation is the fundamental. Okay. Without this, you probably couldn't solve a problem later. Okay.
Quick question.
Yeah.
How are we determine whether the change in area is vertical or if it's a horizontal or vertical bend?
Because you need to know what does the dy is. Your equation is the velocity. See here, velocity is in terms of y. So you know your dA has to have dy in there. Otherwise, you cannot solve this integration. So this is the trick. So when you define the dA, you need to make sure your dy is in that drawing, okay, in that dA you defined. So it has to be horizontal band because the
Right, I
thickness
see.
of this is dy, okay?
So
this
yeah,
is the
so
trick.
the equation regardless of knowing how to figure it out from looking at the picture, if the equation they gave us was dependent on x, then we would want it to be dx.
Yeah, exactly. If the velocity function on x here, you have to put the dx in there for the dA. Okay. Sometimes you have to put both. You know, if the velocity function of dx and the dy, then if it's x and y, then you have the dx and dy in the integration. Okay, so it's problem dependent. Okay, so I guess integrate of this shouldn't be a problem, right? Everybody should know how to do. Okay, so let me give you the value. I'm out of time here. Let me see. The value is chapter 5, right? Okay. Yeah. So turn out to be 20 cubic meter per second. So cell flow rate. Okay, practice it. If you're not familiar with this, I will assign homework problem for calculating flow rate for different shapes. Okay, different channel, different pipes. Okay. So, okay. I guess that's it for today. So tomorrow, Thursday, we're gonna introduce the conservation law, conservation of mass. Okay, it's totally related to the flow rate calculation. Okay, basically is inlet flow rate and outlet flow rate, right? So, okay. Any questions before we leave?
Is there anything you want us to focus on specifically for the quiz Thursday, or just all of chapter 4?
I already assigned like 20 homework problems there. So I guess that's what I want you to focus on.
Professor, is there going to be another project that you give us?
Yeah,
Like after-
there will be another project for the. I probably give you. It should be chapter 5, conservation of mass. Okay.
Is that the,
So
is
I
that
will.
the last, is that the last one?
No, it's not. We will have next one for the chapter 5, then another one for chapter 6, 7, 1. At least two more. Okay, it could be 2 or 3. I think it should probably 2. We don't have much time left. So one for chapter 5 and one for later chapters. Okay. Okay, so yeah, prepare some homework problem. I have chapter 4's problem. The quiz will be similar. If it's not exactly the same, it should be similar. I may change the number or whatever. So it's good to practice those homework problems. Okay, so that's my recommendation.
Oh, is it open notes quiz?
No, it's just like a regular quiz we did. Okay, it should be open, a closed book, closed notes. It's supposed to be, okay. You have to memorize theories, equations. Okay.
Dr. Zhang, are we going to have time to do more than one video project? We only have 3 weeks left of class.
Yeah, the last one maybe during the final week. Let's see. 26, 27 will be the first due. Maybe the next one will be, yeah. How about that? How about I just make okay, let's just make one project and let me wait for a week to let you know the content. Maybe include everything after this. Okay, include all the chapters. I give you a little bit more content to choose from. Okay, yeah, let's make one project if its time is not allowed. When is our final? 6th, right? Is May 6th our final?
Yes.
Okay, so yeah, 3 weeks. Okay, let's just do one more project. So, okay, so I will post the project a little bit later, maybe include all the contents from chapter 5. Okay, chapter 5, 6, 7, and 10. Okay. Okay. So have a good rest of the day. Okay, see you on Thursday.